We will be investigating the concept of a limit in this section. We're really going to take a graphical perspective to understanding this concept initially, and later on we'll start to talk about other ways in which we can determine limits of functions and expressions and such. So that's why you see the title of the section here today is Limits Around the Plane, because we'll mostly use graphs and things to understand initially. We're going to wean off of the graphs a little bit here today as well in terms of being able to find some limits without necessarily having to look at a picture or a visual aid to find the limit. So we're going to start off by recollecting some things that we've already accomplished as we started this journey here in chapter 2. So let's recollect first of all that back in the very first section that we covered so far of chapter 2, so in 2.1, we really talked about two main problem areas. The first motivating thing for us was to be able to determine the instantaneous velocity of some sort of an object that's moving through time, right? So when we did so, we didn't do that directly, right? We really looked at being able to find average rates of change and how those average rates of change are going to be able to converge to the instantaneous velocity if we make the intervals of time become smaller and smaller and smaller, right? And then another different type of problem, but method-wise, the way we found it was the same, was to be able to find the slope of a tangent line, and that tangent line is a tangent to a point on a curve. Right. Okay, so those were our big two things. And then the other big idea that I want to pull out from what we did in section 2.1 is that construction that we used to be able to determine both of those things. And so what we really did is we used the difference quotient to be able to approximate both of those things. In number 1 and number 2. Because in number 1 and number 2, we didn't find either of them directly right away. We were looking at patterns that were happening, right? So we should recall what that difference quotient, of course, looks like. So at the point x sub 0 that we're trying to find the instantaneous velocity at, or the slope of the tangent line to, this is what we end up getting if the increment is h, right? And ultimately, what we wanted to have happen is we wanted to make h get smaller and smaller and smaller and smaller, right? And as that h got smaller and smaller and smaller, we'd eventually hopefully be converging on the instantaneous velocity or the slope of the tangent line at that particular point, right? So looking at that visually, once again for us, if you take a look at the graph that you have right there, if we assume that, say, like, at this point right here, this would correspond to our x-coordinate x sub 0, and let's suppose that we were trying to find the slope of the tangent line at that particular point. We were just taking different other points on the curve and constructing different secant lines, just like this, right? And ultimately, as we construct secant lines that get closer and closer and closer, right, we eventually approach what the actual slope would be. So this idea, this notion of h getting smaller and smaller and smaller, or making our points get closer and closer and closer to x sub 0, is really describing an aspect of functions that we describe as limits, or the limiting behavior of a function near a particular point. And that's what we want to start to really dig into here today. Okay? So what I'm going to do right away is actually give you a definition of a limit of a function. But it's going to be a definition that really is meant for, like, any person to be able to understand. It's not going to be super mathematical or precise enough to actually be a legit definition of a function, but it's going to be a definition that we can at least use to get started, to start to understand some fundamental concepts about limits and being able to find limits initially. Later on, we're going to give a better definition of a limit of a function that's actually sufficiently mathematically rigorous enough to qualify as a definition of a limit of a function. Okay? All right, so I need to kind of give a little bit of a setup to this definition before I actually define what a limit of a function is. So the assumptions that we need to have hold here is we want to have some function. So I'm going to call the function f. So f of x is going to be a function, and then we also need it to actually have output values that exist. And so the word we would use there is that we need to be defined. And we want to specify where it's going to be defined. And so we're going to define that it needs to be defined on some open interval. So on an open interval. And when I say that term open interval right there, ultimately what that means is it needs to be some interval between two numbers where you don't necessarily have to have the endpoints be in the interval, so they could be like open dots like I've constructed, right? So if that was like 3 and 7 using interval notation, we would have parentheses around the 3 and the 7 because we don't have 3 and 7 in the interval, okay? A closed interval, it's sort of the opposite of an open interval, and that would be like where you would have the brackets in interval notation, where then the 3 and the 7 would actually have filled in dots and they'd be included in the interval. Okay, so we don't need that for this definition. We just need an open interval. But not only do we need an open interval, we want to have a particular number in this open interval because that's what we're going to actually try to limit towards. So on an open interval that contains a point C. Now, there's another thing that we need to note right here. But possibly f of x may not, so it may or may not be defined at C itself. So that little notion right there, I will give sufficient attention to later on and explain exactly what that means and how that impacts our ability to find limits and that sort of thing. But that's the true thing. That's a true assumption in terms of limits. Okay. All right. So now let's actually begin the definition now that I've given a little bit of setup right here. So here's what we can say. So we can say that the limit of f of x is L as x approaches C, and the way that we will write this in notation, let me use a different color, and we write this. So LIM to abbreviate limit, and then we'll put underneath that limit that x is headed towards C, and then what we're doing is we're finding the limit of the function f of x as x goes to C, and then it's going to equal L. And so we'll be able to say this, that the limit of f of x is L as x approaches C, and we'll write it as such, if the following holds. If the value of f of x gets closer and closer to L as the values of x take on numbers that are closer and closer to C. Okay. So you just have to think that x is horizontal in a graph, right? And then f of x is like your y, so it's vertical. So what we're basically just saying here is that as the x gets closer and closer to some c number on the x-axis, right? So as we pinpoint horizontally towards some number c, then the function itself should be approaching some particular y value corresponding to that particular c. Okay. All right. It's a lengthy definition. It's a good definition, but it's not a perfect definition. But it's good enough to get us started and understand what limits are. Some things that we want to be able to note here. This is a really, really essential thing that we need to note about limits of functions is that the limit of a function, and let's say f of x, okay, it does not depend at all on the value of f at x equals c. Okay. That does have a lot of connection to what I noted up there about f of x not being defined at c. Okay. So, yeah, what the value of the function is at c has nothing to do with the limit. It's all about the behavior heading towards c, right? So, there's a huge difference between the limiting behavior of a function, and when I say the limiting behavior of a function, if we say that this point right here is c, okay, then as we get closer and closer towards c in terms of x, okay, that is what we refer to as the limiting behavior of the function at c, okay? And that's different than the actual behavior at the limit point itself, okay? Because what's happening at the point itself doesn't really matter in terms of what the limit is at that particular point. We care about what's the behavior heading towards that point than what's actually happening at the point itself, okay? All right, so to really process all this abstract stuff that I've been explaining and such, right, we're going to need some pictures and a lot of examples to reinforce, and ultimately it actually makes this definition make a lot of sense, and actually it's pretty simple once we dig into this, okay? So let's go ahead and look at some examples where we can find some limits of functions, right? Okay, so relatively simple example to begin with right here. So what we're going to try to do right here is look at the graph of this function f. Now, I've given the equation for this rational function here, and then also the graph of it. It actually simplifies to a parabola because it turns out like x plus 2 is a factor of the numerator, so it like divides evenly, and that's why you get the hole that you see in the parabola and whatnot. Anyways, here, what we're going to try to do is we're going to try to, as x approaches, say, -2, try to figure out what f of x approaches, okay? And so if you look at the graph, okay, you can see that -2 is going to be right there for an x value. We're looking at the horizontal x-axis because we're talking about x, right? So as we approach -2, so as you go this way towards -2 and this way towards -2, if you follow the graph, you can see that you're getting closer and closer and closer to actually where that hole is at, and that seems to be at a y value of 5. So it seems like the answer to this question would be that f of x approaches 5. And that turns out to actually be the case, and we're going to do some further investigation into this in just a little bit. So what's really important is being able to know some notation and ways that we can write this. So we can write this in a couple different ways. So one way in which we can write this, is we can say that the limit as x heads towards -2 of the function f of x, we know it's going to equal 5, right? And so that would be one way to express the limit that we have right here. And then another way that's equivalent to what we just wrote is to write this, and then just by replacement, instead of writing the equation f of x right there, you can just replace it with what f of x is equivalent to, which is of course that function x cubed minus 7x minus 6 all over x plus 2. Okay, the limit of that expression as x heads towards -2 is also going to be equal to 5, right? So either of those two ways are fine. You don't need to write both. More often than not, we'll probably write the first one just because it's a little simpler and a little bit shorter, right? So ultimately, the best way to kind of justify what I was showing right here and right here is to really generate a table of values, and use a table of values to kind of inform what the limiting value is right here. So what I'm going to do first of all here is in the middle of the table, I'm actually going to put in -2, but keep in mind, we don't actually care about the function value at -2 itself. Now, if we were to actually, plug -2 into the rule right here and do -2 cubed minus 7 times -2 minus 6 over -2 plus 2, you're going to get whatever number divided by 0, which then becomes undefined. So it actually turns out that in this particular example, f of -2 doesn't exist at all because there's a hole right there. Okay, but even if there was a number right there, that wouldn't even matter in terms of the limit of the function, right? Because as I said earlier, the value of the function at that point does not matter at all in terms of what its limit might be. So what we want to try to do here is we want to try to see what's happening as the x values get closer and closer to -2, and we're going to do this from both sides. So looking at function values lower than -2 and then function values that are higher than -2. So we might start at like -3 because it's kind of close to -2. It's only one away, right? And ultimately just plug in -3 into that function, okay? So I would use a calculator and evaluate what that's going to come out to be, whether you have a graphing or scientific or whatever. And when you plug it in, it's going to end up becoming 12, right? Now you'll want to plug in things that are probably a lot closer to -2. So -3 is probably not a good starting number. What would be maybe a little bit better is something like -2.1, which is definitely a lot closer. Okay. And you plug that in and you get like 5.61. And then I would plug in some numbers that are closer to -2, like this, and then -2.01. And then if you plug all of those in, you're going to get here we go. That's accurate. That value right there, and then that value right there. And so what's important to see is that as the x values, right, you can see that x is going toward -2. Then right here, these are all the y values, and you can see that going from 12 to 5.61 to 5.3025 to 5.0601, it seems to be going towards 5. Right? Now, to actually legitimately confirm like what we're seeing here, we want to also look at this from the other side, so from values that are higher than -2. So to kind of do this symmetrically, you could like put -1 right there, and then you want to get a lot closer to -2, so like -1.9, -1.95, -1.99, right? And plug all those numbers into that function f that we were given as well. These would be the values that you end up getting. It's actually, basically the same values because, our parabola is symmetric, I guess, right? And so you can see that this way, right? This is where x is headed towards -2. And then it seems that f of x right here is headed towards 5 at that same time. And so therefore, that table of values really gives us the intuition that we're probably actually, right about this. And indeed, that is the limit, okay? So realize that what we did there is not really the perfect way of finding a limit. There's actually good algebraic ways for us to prove what the limit is, but we'll get to that later. So as I said today, we're really just looking at this graphically and understanding the notion of what limits mean and such. Okay, so let's try to do this without an equation to even work with and just go straight from a graph to be able to evaluate limits of functions, right? Okay, so right here, we want to use the graph of the function to find the indicated limit, and you'll see that we want to find the limit as x goes to 6 of the function g sub 1 of x, which you see in the graph over there. So what that would mean then is right here is where we have 6, right? So we want to find what is happening as we follow the graph on either side of 6. So as I follow the graph this way, and then if I follow the graph this way, what are we converging to as we get towards 6, right? And if we follow up to here, we'll see that on both sides of the graph, we seem to be converging to basically the same y value, which looks to be 9. And so we'd be able to pretty confidently say that the limit of the function g sub 1 as x heads towards 6 is 9 in a case like that. Okay? All right, so as we look at the next example, it's going to be almost like the same thing. Okay? But the only difference, though, here in this example is there's just a little bit of a hole that you're seeing in the function. So all that matters with the limit of a function, right, is just what values you're approaching as you get closer and closer and closer, right? Not the actual function value at the point itself. So even if there's a hole right there at 6 in this particular case, that's not going to matter because you can see that as we get closer and closer to that point where x equals 6, the y values are headed towards 9 from both directions. So it turns out that, once again, the limit is 9, right? And then for a third example, now we still have the hole, but now we've actually made sure that the function is defined at the point 6, but it's like, way down there, right? Ultimately, again, all that matters in the limit of the function is that if we follow the function from the left of that 6 and from the right of the 6 and get closer and closer and closer, right? It's headed toward 9 on both sides, right? And so, like, that random point right there has nothing to do with the limit of the function, right? Because the function value at that point is completely separate from what the limit is. And so the answer here, again, is going to be 9. So the big moral of the story with all three of those examples is just understanding, right, that the value of the function is not relevant to limits of functions. Okay. Sometimes the value of the function is the same thing as the limit of the function, and that's a different thing that we'll talk about at a different day. Okay? All right, so I mentioned earlier towards the beginning that we really want to try to detach ourselves from graphs a little bit here today as well. And so here we're asked to create a table of values to be able to estimate the value of the indicated limit without necessarily having to graph the function or look at the graph. So that should definitely be something that you're able to do. So we're trying to find the limit as x goes to 4. So first of all, just, for funsies, let's see what happens if we plug in 4. Now, if you plug in 4, you'll notice that the denominator would become 0 and undefined. So it's actually an example where, it doesn't exist. So what really matters for us is looking at as the x values get closer and closer to 4 from both directions, what's going to happen with our y values in terms of the same, tendency. So let's pick some numbers that are actually closer to 4, because I picked earlier numbers that were like 1 away to begin with. So maybe for like numbers lower than 4, maybe let's start like 3.8, and then we can do 3.9, and then 3.99, and 3.999, let's say. And then you'll just need to plug them into that function and use a calculator accordingly. When you do so, you're going to come up with these particular values, particular y values. Sorry, put too many zeros there. That should be 0, 0, 1. There we go. And then if we were to do this coming from values higher than 4, we could do 5.2. 4.2. 4.2, 4.1. 4.01 and 4.001, how about, right? And you will end up getting then these y values, okay? So it seems that, right, as the x values here are headed towards 4, the y values go from 0.2 to 0.1 to 0.01 to 0.001. So it seems to be headed towards 0, right? And then right here also heads towards 0, right? So basically we're seeing from the left side of this that as x approaches 4, then on the right side we're seeing that h of x is approaching 0. Right. So what we'd be able to conclude from this then is that the limit of the function h of x as x goes to 4 seems to be 0. And that actually is legitimately true in this particular case, right? Right, so now we need to start talking a little bit about some cases where, when we're trying to find limits, that the limits might fail to exist in some particular cases. And so that's what we're going to start to examine next here. So you see this function here, k of x, which is equal to the sine of 1 over x. We want to explain why the limit as x goes to 0 of k of x does not exist. Okay, so you do have the equation, and then I also have the graph of the function down here. So what's interesting about this function is that if we're trying to find the limit as x is going to 0, then we're trying to move from the right and from the left and follow the function values, and you can see like it starts to, like go up and down a whole bunch right there. Okay, I'll talk a little bit more about what's actually happening there in just a little bit. I think it would be really, really helpful for us is to look at a table of values and see what's going to happen here. Now, if we were to plug in 0 itself and then try to do sine of 1 over 0, 1 over 0 itself is undefined, and so, trying to put something undefined to sine isn't going to work. So, lo and behold, k of 0 does not exist, right? Okay, so let's try to approach 0 from lower numbers. So we could try to approach this from, say, negative 1/10th and a negative 1/100th, negative 1/1000th, and negative 1/10,000th, and see what function values we end up getting. Okay, so you'll want to plug this into a calculator. You would need your calculator to be in radians to appropriately get the correct values. When you plug this in, you're basically going to get values that are about these numbers. So it seems relatively okay to begin with, but then all of a sudden it jumps to negative 0.826 and then 0.305. Um, and then if you kept even choosing smaller and smaller and smaller numbers, like negative 1/1 millionth or something, it keeps jumping around a lot because ultimately what's happening right there is it keeps oscillating up and down infinitely as it gets closer and closer and closer and closer to 0, and it just infinitely oscillates like that. So it never really converges onto a particular y number. It just keeps going up and down and down forever, right? And so, if you were to fill in the other side of this table right here and look at some positive numbers that are headed towards 0 x y's, and then look at the y numbers, there really wouldn't be a pattern in the y numbers, even though the x numbers would be following a pattern as you get closer to 0. Yeah, so basically, just to keep this simple right here, the k of x values are really just oscillating between actually negative 1 and positive 1 for y values as x is headed towards 0. And so because of that behavior that we're seeing right there, the limit of the function k of x is headed towards 0 is just not going to exist. Okay? All right, so here's another example where we'll also see a limit fail to exist. So m of x is equal to 1 over x minus 3 squared plus 4. And what we want to try to do is we want to try to find the limit as x goes to 3 of m of x. Okay, so if we were to actually plug in 3 itself into the function, you'd have 0 on the bottom. And so then it'd be undefined, right? So it's actually not going to be able to exist. Okay. Now, what's going to actually happen here is if we were to plug in, say, 2.9 and 2.99 and 2.999 and then 2.9999, okay? You can kind of see already what's going to happen because, if this is where 2.9 is and then 2.99, it keeps getting higher and higher and higher. So I don't actually like these are not going to be the actual numbers because I don't have a calculator on me right now to get the actual numbers for this particular problem. But let's just pretend let's say it's at 104 right there. and then maybe this is like 10,406, and then this is like a million, and then all of a sudden this is like whatever, however many more zeros, right? Ultimately, it keeps getting higher and higher and higher and higher, and so it doesn't really converge towards any particular one number, right? It just keeps growing without bound. So like it's headed towards infinity ultimately what's happening, right? Because there's this asymptote right there. So those graphs are keep getting higher and higher and higher. So the y values keep increasing. So you'd basically see the same thing happen if you had 3.1 and 3.01 and 3.001 and 3.0001, right? You'd have like the same numbers could be symmetrical, but you know that my numbers are not accurate, right? And so, yeah, it'd be headed towards infinity and that sort of thing. So, basically, in a nutshell, what we'd be able to say here is that the m of x values, they are growing without bound as x is headed towards. Okay? We will be able to give some attention to the fact that they're headed towards infinity and deal with that appropriately with limits in a little while. Okay. All right, and then a third example before I just kind of summarize some things about limits failing to exist is this particular example right here. And so what we have right here is we have the function p of x, which is equal to, and then you can kind of see some interesting symbols around x right there. So what's happening is you kind of see this staircase function. What this particular staircase function is doing is, let's say that like you send in a number like 1.5. At 1.5, you actually have a y value of 2. So what it's doing is it's just taking any like decimal number and like rounding it up. So this function is what we call the ceiling function, because if you think of it like a ceiling, like it's above you, so you're always like rounding a decimal number up. So even like 1.1 is going to get rounded up to 2, right? So you're always just like going to the next integer higher than the number, always in the ceiling function, okay? So we want to try to explain why this limit as x goes to -5 of p of x does not exist, right? So at -5 itself, so at -5, you can see there's an open circle and then a filled in circle right there. Actually, we do have a function value existing right there. It's actually -5, right? Now, if we were to look at values that were lower than -5, so let's say like negative 5.1, -5.01, -5.001, -5.0001. Okay, we're really looking at heading this way towards -5 from the lower end. And what's always going to happen is the y values are actually all going to be down here at -5. Okay, so right now it seems okay because like -5 is all headed towards -5. But then if we go from the right hand side and we plugged in say -4.9, -4.99, -4.999, -4.9999, okay, then all the y values are actually on this step right here, which is at a y value of -4. So the y values there are all -4, right? And so it seems like they should be headed to -4 from one side, but headed towards -5 from the other side. So there's no agreement from both sides. And so that's why we kind of don't have a limit existing. And not kind of, there is no limit that's existing at -5 right here, right? So in simplest terms right here, we just have different values that are approached. Um, from both sides of x equals -5 for this particular function, p of x, right? Good, good, good. All right, so let's just bring some of that knowledge together here and talk about where limits are failing to exist. So to just define this, we will say that the limit as x goes to c of f of x will fail to exist when, as the x values get closer and closer to c, then the value or the values of the f of x do not approach any one particular um, value, right? Beautiful. Okay, so let's talk about some reasons why a limit is going to fail to exist. So, some possible ways where a limit might not fail to exist is if there's going to be no function value that is being approached as x goes to c. Okay. So that's best exemplified, and what's intended right there is to talk about what's happening here in example four, because we weren't any approaching any particular value, right? Because it was oscillating and that sort of thing, right? So you can kind of refer to what you're seeing in example four for what you're seeing there, right? So another thing that could happen right here is that the function would be growing without any bound to it. And so that was exemplified back in example five as, it headed towards like infinity, right? And the same thing could happen. It was headed towards like a negative infinity too, right? And then a third thing that would cause a limit to not exist is if there was like a jump in values in the graph. And we just saw that in that step piecewise function, how there was a jump at -5 occurring right there, right? So if you refer to example number six, you'd be able to get that. Okay, here I maybe want to make some remarks about what was happening in example number five. What we are able to do is we can say the limit as x goes to c of f of x equals infinity, or we could also say, if it was headed downwards from both sides, that the limit of f of x as x goes to c would equal negative infinity if f of x grows without bound as x goes to c. Okay, so we can write that notation, but the important thing that you should realize though is that even though we write that, note that the limit still fails to exist in these cases where it tends towards infinity. Okay, so like for a limit to exist, it needs to approach a particular real number, right? But it is actually preferred that in the cases where it is for sure going towards an infinity or negative infinity, that you just say it equals infinity and equals negative infinity. Do that, please, but just know that in those cases,